Clean Space. Hello everyone, welcome to Clean Space Robotic Active Debris Removal demo from Surrey Space Centre at University of Surrey. My name is Yang Gao. I'm Professor of Space Autonomous Systems, heading the STAR Lab, and here are my team.
Hi everyone, my name is Nikos Mavrakis and I'm a research fellow at STAR Lab working on robotic grasping for orbital applications.
Hi, my name is Richard and I'm the Technical Officer for Fairspace.
Hi, my name is Alexander Masowski. I'm a technician. I help researchers to run experiments.
Hello, my name is Daniel Johal. I'm a research fellow working at STAR Lab on Fairspace project. My job is how to drive spacecraft smartly. Okay, here you go, Yang.
So I'm going to give a very quick introduction about the background of the demo. So as people know, at the moment, our planet Earth is surrounded, orbited by a lot of space junk, or we call space debris. They could range from the span motor with nozzles, like the model I'm holding right now, or retired satellite, such as this kind of CubeSat system, and they're really harmful to the existing space assets, such as satellites that is providing satellite navigation or satellite TV. So it's important and critical for us to develop robotic and artificial intelligence solutions to help autonomously run when dock and capture, remove this kind of type of object in orbit. So in this demo today, we're going to use the target, which is like the model I'm holding right now, because it's relatively more challenging for robotic grippers to capture because of the curvy surface. And also you're going to see different rounds of trials so that you can see how the decision-making systems on board the robot could decide in real time whether it's safe or not safe to proceed. And this is very important to secure the safety of our spacecraft equipped with the robotic arms. And I would also like to take the opportunity to thank Fairspace program, which funded the research behind this demo, as well as UK-RAS Network, who created the opportunity for us to engage with you guys today online live. Hope you enjoyed the demo. See you.
See you.
Okay, it's Daniel here. I'm taking it over as a producer, and along with my colleagues, Nikos. Nikos, do you want to say hi again?
Hello everyone, hi again.
Okay, so Nikos, what we're going to show to people today, can you give us another recap, very quick one?
Well, yes, as Yang mentioned, today we're going to show a demo execution of a robotic satellite attempting to capture a piece of space debris, which basically is an apogee motor. And an apogee motor is basically the top part of a rocket, and its purpose is to place the satellite, the payload, as we say, in its final orbit. And they have not been designed to deorbit naturally. So we have to develop some very novel methods to actually attempt to capture them and deorbit them. Some of these targets can stay in orbit for up to 25 or more years, as some of them they are still in orbit ever since the 60s. So this demo today is about, again, as I said, attempting to capture such a satellite. And you will see pretty much what we are attempting to do in a simulation now. So Daniel, would you mind playing the simulation? Thank you. As you can see, the shiny part is the apogee motor, so the top part of the rocket. And the yellow part of the simulation is the chasing satellite, which is equipped with a robotic arm and a gripper. The task that the robot needs to do is to get close to the piece of space debris, so the apogee motor, and find out a good capturing point in order to execute the capture. As soon as it executes the capture, it needs to pull the target back for a specified distance, as you can see on the demo. And one of the technologies we have been developing in Starlab is actually the autonomous method of finding out a good grasping point. So now, how does the robot know where exactly to capture the satellite? It can capture the satellite by calculating a point cloud of the object, as we say, of the target. A point cloud is basically a pattern, a light pattern that the sensor shoots to the target, and then it measures the distortion of this pattern. This distortion is translated to distance from the sensor, and then it's translated to a point. So each point of the point cloud represents the distance of each part of the target from the camera. And we use this point cloud to extract the grasping point from the target. You can see an execution of the algorithm here. So Daniel will show you a video of the execution. This is exactly the execution, as you can see. So this is me going around a mock-up of the nozzle with the sensor. And you can see on the top left part, the grasping points, which are represented with these coordinate frames, as you can see. They are being generated for the point cloud almost instantaneously. I think we have about 0.25 seconds for 25 or something grasping points. And as you can see, the algorithm, as I said, is very fast and quite reliable. So you can see the speed of the calculation of the grasping points. And the robot then picks one of these grasping points as the most suitable grasping point to capture the piece of space debris. So to bring all this technology back to Earth, because it's not very easy to test it in a real space. Yeah. We need to have a test bed that mimics exactly to the extent of possible, the orbital environment. And you can see the testbed in your screens now. So Daniel, would you mind telling us what the testbed includes?
Yeah, of course. Thank you, Nikos, for the introductions. As you can see from the picture on the left-hand side, that's a live streaming video and showing our testbed over here. We call it orbital robotic testbed. So what does it do? It actually simulates this simulation with the hardware in the loop. So the traverser, which on the left-hand side, you can see the track system, is simulating the servicing spacecraft as a yellow cube showing on the simulation. And we have a UR5 arm sitting on top of the traverser. You cannot see now, but you will see it in the demo because the field of view of the camera. And on the right-hand side, as you can see here, we have the target, which is the nozzle holding by another UR5 arm, which use the 6th degree of freedom to simulate a microgravity simulation in space, which means if we move the nozzle around, if we touch it, it will float or move as in a microgravity environment. We do have a video to show people, right, Nikos?
Yes, exactly.
Yeah, that's what we do the testing, as you can see here. Nikos, do you want to give a bit more recap on this?
Yes, exactly. So this is me having some fun with the nozzle here. And what is happening is that the target arm, this arm that you can see there, is equipped with a force sensor. So it is able to actually sense the amount of force I'm putting on the object. And then it drives this force through a simulator that simulates the motion of the target as if it was in space. So then this motion is fed back into the robot, and it's precisely followed by the target arm. So we can then mimic a weightless environment for our target. This system is quite responsive, and you can see that it will perform well.
Okay, now I guess enough of talk. Let's go to the exciting parts to show the live demo. Okay, so as you may know, remove a debris in space is not just capturing it, but also as well as rendezvous. And imagine if you have a target at far distance, you need to approach it. So the first part of testbed is the traverser, which is simulated service spacecraft. So we're moving into a state which we can have a better measure of the point cloud for the target. So as you can see now, the spacecraft start moving, approaching to the target. You can see now the traverser and with the arm is slowly approaching the target to get to the stage 1. And also you can see from a second screen I'm showing here, you can see that's the live streaming of the point cloud from the camera. Nikos, do you want to give a bit more introduction on this part?
Yes, exactly. As I mentioned before, the sensor shoots a light pattern to the target, and you can see this light pattern, the result actually of this light pattern on the top screen, on the top left screen. And the bottom left screen is actually a camera, the camera feed of the sensor. It also has an RGBD camera, so the chasing satellite can exactly see what is going on with respect to the target. And to the right, you can see the point cloud, the generated point cloud, as I mentioned before. You can see that there is also the wall in the back of our test bed, but this is not calculated, taken into account for the calculation of the grasping point.
So Nikos, let's move to the pre-capturing state. Is that all right?
Yes, definitely.
Yeah, sure. So as we have more information about the target, now we are safe to approaching to the pre-capturing phase, which means we'll be closer to the target. And at the same time, we can get a better image of the point cloud as well. As you can see, the point cloud is to keep updating as well. So now we are ready for capturing, right, Nikos?
Yes, definitely. Before we execute the capturing, we need to discuss exactly what the potential outcome will be. So the chasing robot will attempt to capture the surface of the nozzle to a calculated point that it will calculate, and it will attempt to pull it back for a specified distance. We're not sure whether exactly it will succeed or fail in actually retaining the object for the whole duration of the pull. And this is something very exciting that happens every time. So there is a chance that the robot actually captures the object and maybe does not capture the object. So let's execute the demo.
So let's see.
And see.
So now Nikos is running the program now. As you can see, now the arms start approaching to the target and find the grasping point and do the gripping and start doing the pulling motion, I assume, Nikos.
Yes, exactly. You can see that. Oh,
Nikos.
the robot actually did not succeed this time. So it lost contact with the target and it will now return to its original position. That's okay, it happens. It's natural for these type of things to happen because actually attempting to capture pieces of space debris, it's extremely challenging. There is a lot of reasons that it can be very challenging. So we can...
Let's try again, Nikos.
Yes, we can do one more execution.
Let's see what's going on this time, Nikos. Okay, now we're doing the execution again. So it's approaching to the target and do the gripping again. Hopefully this time it will work. Nikos.
Yes, let's see. As you can see, it found a different grasping point. And it starts pulling. Now I see.
Oh, I think this time it's successful.
That looks well. Oh, that went well. So at this execution, the robot managed to actually capture the object successfully. So it did not lose contact.
Looks contact. Okay, Nikos, as mentioned before, it's actually very challenging. Do you want to give another try? Let's see how's the result this time.
Yes, definitely. Let's see what's the result this time. As you can see, the robot was on a different grasping point. The robot will then execute the motion. And no, this time it failed. But these things happen. It's natural for these things to happen.
Yeah, that's why it's so challenging to do such a work in space, right? So I saw we have quite a few audience here. Is there any question for us?
Actually, we can give a couple of reasons of why is it so challenging to do this capturing and attempt for the whole duration. It's because sometimes the friction between the finger and the target surface is quite high, and this happens both in space as well as in environmental conditions. And sometimes the gripper does not succeed in applying a continuous force all the time. So just because we command it to apply this force, the changes between the poses for the target and the gripper result in application of less force.
Yeah, thank you very much, Nikos. So we have a question come through from the audience. His name is Patrick Hothos, and he's asking, that looks very cool. Would you also be able to simulate the movement of the debris in the approaching phase and immediately before grasping?
That would be interesting to do. So if I understand the question, so simulate the movement of the debris in the approaching phases. What we're doing is, for this particular demo, we are considering that the target and the chaser, they are synchronized and they have matched their relative velocities. If we consider the target as a single entity, then it tumbles in space. But the chasing satellite needs to have matched the rotation of its body to the rotation of the target, let's say. In some cases, it is possible to do. So we have some other types of research that are looking into pose estimation and the motion estimation of tumbling targets. But for the purpose of this demo, we consider that the chaser satellite and the target have matched their relative velocities. I hope this answers the question.
Well, thank you, Nikos, for the answer. So hopefully that answers the questions. So do we have more questions come through? Yeah, Nikos, yeah, we have follow-up comments. Do you want to
Yes,
say a
definitely.
few words about this?
It's actually in the rendezvous phase, the spacecraft is actually responsible for making this type of calculations. So estimating a lot of properties of the target, let's say the mass of the target, the position of the target, the relative pose with respect to the chasing spacecraft, and the rotational velocity of the spacecraft. And in the proximity phase, which is typically in the range of a couple of meters. So basically,
It's quite risky if we do all the things, where the grasping.
yes, exactly.
Still synchronize the motion.
The job that the robot needs to do in the proximity phase, which is basically a couple of meters to a couple of centimeters away from the target, is to identify a good grasping point, having identified all the initial properties of the target in the rendezvous phase. The rendezvous phase can be up to a couple of kilometers away from the target.
Yeah, I hope that addresses the follow-up questions. So, well, thank you, guys. Do you have any other questions coming through? We can, Nikos, do you want to give another try? I mean,
Exactly.
yeah, we can give another try.
See whether this time it will be. Oh, that's a solid put. Oh no, that's a pity.
So, yeah, I think it's okay. It's almost there.
Yeah.
Yeah, and you can also see the live streaming of the point clouds on your right-hand screen as well. As mentioned before, the testbed we are trying to simulate. We're using the light-absorbing materials, trying to simulate the space lighting conditions. So another problem for doing this sort of job in space with computer vision is the extreme lighting environment. Is that right, Nikos?
Yes, exactly.
So, for example, the infrared lights can fully affect the point clouds, the quality of point clouds. So sometimes you need to use some special qualified sensors, have some pre-filtering, and some algorithm to compensate those things as well.
Exactly. So it's very typical that the point cloud is quite messy with a lot of noise and a lot of holes or missing parts. And it's natural for an algorithm to try to work around these issues by working with the point cloud that it has, or even employing other modules of other modes of sensing, such as RGB cameras, and perhaps LiDAR sensors, which are another sort of laser sensors that are rotating and calculating distances, and so on and so forth. It's, as we said, it's a very challenging problem.
It is. That's very interesting research areas. So I think we still have 5 minutes for questions. Please feel free to ask any questions. We would happy to answer for you.
Well, in this case, we can mention other types of research that we do in StarLab, especially in this type of environments. Basically, these nozzles are also parts of working satellites, not only space debris or defunct satellites. And these nozzles have been identified also as a potential contact point for satellite servicing. So there is this new domain that involves servicing satellites, so capturing working satellites to perform tasks such as refueling and many other things that involve fixing a satellite. And these nozzles have been identified as very good grasping points because they're very sturdy and they are present in most of the satellites in orbit right now. And we also do other research in pose estimation, as we said. We have some novel deep learning methods that estimate the pose of a space debris or a CubeSat, as it was mentioned in the beginning of the demo. And we can estimate the relative pose in different lighting conditions and using the synthetic data from high caliber simulators and our testbed, of course.
Yeah, thank you, Nikos. I think we still have 3 minutes, so we can quickly show you another video, which is with a cooperative target. So just give me a second. Let me loading this video. Okay, so as you can see from here, this is a very typical orbit assembly structure with universal connectors. So in this research, we are comparing the traditional AR marker method with our deep learning method to do the on-orbit assembly work. So we only use 2D images instead of a point cloud in this work. So this is about autonomously assembly. So it does get to the pose of the target and then do the approaching phase as well as docking to make sure it can accurately and robustly makes the connection with the assembly structure. I think we also got a new question.
Yes, we have another question.
Right?
Yes,
so the
exactly.
question asks, what's the size of the spectrum debris can be found? It's a very good question, Nikos.
Yeah, exactly. And space debris can be found in many different shapes and sizes. So basically, these types of debris that we are dealing with are categorized as over 10 centimeters. And they can be ranging from a couple of, let's say, centimeters, tens of centimeters, to a couple of meters, sometimes more than 5 or 6 meters. And there is also the problem of debris that are smaller than this scale. And the numbers of space debris are astonishing. So let's say for this particular case that we are investigating now, almost 18% of all pieces, let's say, of space debris are this type of rocket stages. So you can see that it's very crowded up there. We need to do something, and we need to produce some very good research on how to actually clean the environment in orbit.
Yeah, certainly. Hope that answered the question.
I believe it answers the question.
So the answer is can vary a lot, the size. So I guess it's about the time. Thank you, guys. Thank you very much for being here today.
Thank you, everyone, for attending.
Okay, we are running 3 more sessions, maybe in 10 minutes, I guess, if you have the schedule. So thank you, guys.
Thank you, everyone.
Bye.
Hello, everyone. Welcome to Clean Space Robotic Active Debris Removal demo from Surrey Space Centre at University of Surrey. My name is Yang Gao. I'm Professor of Space Autonomous Systems, heading the STAR Lab, and here are my team.
Hi everyone, my name is Nikos Mavrakis and I'm a research fellow at Starlab working on robotic grasping for orbital applications.
Hi, my name is Richard, and I'm the technical officer for Fairspace.
Hi, my name is Alexander Masowski. I'm a technician. I help researchers to run experiments.
Hello, my name is Daniel Johal. I'm a research fellow working at Starlab on Fairspace project. My job is how to drive spacecraft smartly. Okay, here you go, Yang.
So I'm going to give a very quick introduction about the background of the demo. So as people know, at the moment, our planet Earth is surrounded, orbited by a lot of space junk, or we call space debris. They could range from the span motor with nozzles, like the model I'm holding right now, or retired satellite, such as this kind of CubeSat system, and they're really harmful to the existing space assets, such as satellites that is providing satellite navigation or satellite TV. So it's important and critical for us to develop robotic and artificial intelligence solutions to help autonomously run and dock and capture, remove this kind of type of object in orbit. So in this demo today, we're going to use the target, which is like the model I'm holding right now, because it's relatively more challenging for robotic grippers to capture because of the curvy surface. And also you're going to see different rounds of trials so that you can see how the decision-making systems on board the robot could decide in real time whether it's safe or not safe to proceed. And this is very important to secure the safety of our spacecraft equipped with the robotic arms. And I would also like to take the opportunity to thank Fairspace program, which funded the research behind this demo, as well as UK-RAS Network, who created the opportunity for us to engage with you guys today online live. Hope you enjoyed the demo. See you.
See you.
Oh, sorry, guys. I just forgot to unmute my microphone. Yeah, this is Daniel again, and with my colleagues, Nikos.
Hi everyone, this is Nikos. Nice to see you again.
So as you can see now, the screen is showing a live streaming of the camera facing to our orbital robotic testbed at Starlab at Surrey Space Centre. So today, what we're going to show to the audience, Nikos, can you give us a brief recap to it?
Yes, definitely. As Yang mentioned before, we're going to show a demo of an active debris removal scenario where we have to capture an apogee kick motor. An apogee kick motor, as you can see in this simulation here, is it's a piece of equipment that comes with every rocket launch, and its job is to place the payload, so the satellite, to its final orbit. After placing the satellite to its final orbit, it tends to stay in orbit, so it is not made to naturally deorbit. And some apogee kick motors can stay for up to 25 years or more, as far as I remember. So you can see that is becoming an issue with these types of space debris. And you can see that the apogee kick motor is the shiny silver part of the simulation there. And the yellow part is the chasing satellite. So it's our satellite that is tasked with capturing and removing this piece of space debris. The chasing satellite is equipped with a robotic arm and a gripper, and its task is to identify a good grasping point on the apogee kick motor, because the target again has not been designed to be captured. So the chasing robot needs to find out a good way to make a grasping point. And the way it does that is actually with an algorithm that we have developed on Starlab, which uses a point cloud of the target. A point cloud is basically a light pattern. We use a sensor that shoots a light pattern and measures the distortion of this light pattern to translate it to distance from the sensor. You can see actually the execution of the grasping algorithm here in this video. So this is me going around a mock-up, a 3D printed mock-up of the nozzle. And you can see that the grasping points are generated in the top left part. And they are represented with these coordinate frames of blue, green, and red. You can see that the algorithm is quite fast. So we have a couple of statistics we have is about 0.5 seconds for about 25 grasps. And you can see that the final point is then selected from this bunch of grasps, and the robot can go on and reach it to the orbit, the piece of space debris. In order to emulate all these conditions, so we have our testbed, as Daniel mentioned. So, Daniel, would you mind telling our audience what does the testbed consist of?
Sure, certainly, Nikos. Thank you for your introduction about the point clouds and the technology challenge we are facing at the moment. So we have designed and built this testbed for doing experiment for orbital robotics. As you can see, we have on the left-hand side, we have a traverser system, which is 2 degrees of freedom, which is simulating, as you can see from my screen now, is simulating the simulation we showed before, the service spacecraft, as the yellow box is showing in the picture, in the video here. And on top of the traverser, we have a UR5 arm, which is represent the servicing spacecraft arm to capture the target. Of course, on the live stream video, you can see we do have the target, which is holding by the target robotic arm, which is another UR5 robotic arm. Is covered by some black materials around the room, which we're trying to simulate space lighting conditions. Outside the camera frame, there are also light hanging on the roof, which have the similar spectrum as the sunlight. We can adjust the brightness and intensity of the light to simulate different lighting conditions in space. That can be really critical as well. So, as I mentioned before, for the service arm on your right-hand side, sorry, for the target arm, it carries the target, which also simulates free floating condition in space, which means we lift off the weight of the target and we use the arm to simulate the microgravity conditions. So as you can see here, my colleague Nikos is trying to play with it and it actually moves with his hand. He will give you a bit more explanation about this, Nikos.
Yes, sure. So you can see me having some fun here with the target object in this video. So what you see there is the target arm, which is equipped with a force torque sensor. And this force sensor actually reads the force I am applying with every hit. So this force is then projected into a simulator that simulates the motion of the target as if it was in space in a weightless environment. And this motion is fed back to the end effector of the robot, so that it emulates this motion in reality. And you can see if you take your eyes, if you put your eyes, let's say, on the target, you can imagine that it moves as if it was in space.
Yeah, it actually take a while for people to understand what's going on here. Exactly. So I think let's now move into the most exciting parts, right, Nikos?
Yes, exactly.
Okay, so as I mentioned before, so removal debris is not just a simple grasping and pulling motions, but as well as involve lots of research on rendezvous and approaching to the target. So at the start of our experiment, as you can see, we have the service arm, unfortunately outside the field of view of the camera, but it's located quite far away from the target. And in this demonstration, we now moving to a more close position to have a better examination of the target. As you can see from the right-hand side, that's a point cloud of the target. As you can see, once the arm is getting closer to the target, the quality of the point clouds is getting better. And also from the image information, we can get a better idea about the target, what's the rotation speed, and how far from the service spacecraft. And we can synchronize the motion of the spacecraft with the target and then do the final approaching phase. So now we assume everything is safe, and then we can move to the final stage, which is a pre-grasping state. Okay, Nikos, I'm now moving to my colleague Nikos, and he will explain you the cool part of the grasping.
Yes, exactly. So what are we going to see now is the left robot, so the chasing robot, attempting to find out a good grasping point on the target, so the nozzle. You can see there the point clouds as Daniel described, so you can see the depth information from the structure light on the top left panel, and you can see the RGB camera feed in the bottom left panel. You can see the generated point cloud also on the right panel, so this is exactly what the robot sees. And it will attempt to create a grasping point, move on to this grasping point, close its gripper, and pull the target back. If the robot retains the target for the whole duration of the pull, then we'll say that the grasp is successful. Otherwise, if for any reason the robot loses contact of the target, then the grasp is deemed to have failed. We'll execute a couple of demos now, and hopefully all of them will succeed. There is a chance that all of them will fail, but we have to stay positive for that. So Daniel, I don't know if you're ready. We can start the execution of the main demos.
Of course, I'm ready. Hopefully the audience are ready as well. I mean, Nikos, go ahead. Let's do the exciting part for the grasping.
You can see the robot going on to the approaching point, then attempting to reach the grasping point, closing the gripper, and let's see, the moment of truth is here. As you can see, there is a sort. Oh, okay. So the robot in this time did not actually succeed to capture the object because, as you can see, the object slid from the fingers. That's okay. We can try again. So Daniel, if everything is ready, we can try again and see if the robot is actually going to do it this time.
Yeah, sure. Let's Nikos, are you ready? Let's try it again. See this time. Okay, Nikos, can you run the algorithms now?
Yes, sure. So you can see the robot actually finding a different grasping point and attempting to capture the target. And we have a capture. And there is a pull. Oh, this time, okay, I think this time the robot made it.
Oh, yeah.
So that's
congratulations.
Good.
Yeah.
It was a good call this time. So I think the robot was able to hold the target for the whole duration of the pull. And this is very exciting because it's more often that we fail to capture something in space because it's very challenging, rather than we succeed in capturing something.
Yeah.
And
okay, so just out of your curiosity, Nikos, I'm also curious. Can we do another try to see if it works or not?
Yes, definitely we can. And we'll command the robot to see if it can find another position right now. So we can see again the robot moving on to the approaching point, to the grasping point, closing the grasp, and attempting to capture the target, which is, it failed again.
I think it's pretty good, actually.
It was pretty good, yes. It was pretty solid again this time. I think it failed by a very narrow margin.
Yeah, okay. As you can see, it's actually a very challenging task.
Yeah, actually, attempting to capture satellites and space debris is very difficult because of a number of reasons, basically. The number one reason is the friction coefficient between the fingers, the robotic fingers, and the target. Especially in space, this friction tends to be increased, and it's very difficult for the robot to retain its grasp after it has captured the target. Another reason for failure is that the robot, so the robotic reaper, fails to apply a continuous force, a very strong force for capturing the target all the time. The relative position between the target and the chasing arm makes for this force to not be applied continuously. So the robot, let's say, relaxes its grasp with respect to the target.
Yeah, thank you, Nikos, for explanation. I think we can answer a few questions from the audience, right?
Yes, definitely. So if there are any questions from the audience, there is always a good time to
Yeah,
let
of
us
course.
know, and we can answer any questions you can have on our experiments, on the test bed, on our research in general.
Yeah, and my colleague Alex is here as well. He can also answer your questions. Okay. I think Nikos, there was for the last round, there was a question was asking, are the gripper size affect the effectiveness of the gripping algorithm as well, right?
Yes, actually, there was a question like that, and I think it's worth mentioning. And this robot right now has some fingertips of a rounded shape. And our research in Starlab has shown that it's more beneficial to capture something of this conical shape with rounded fingers instead of planar fingers. This happens because the round, let's say the rounded shape of the fingertips tends to match the surface of the nozzle. So it yields a grasp that has more chances of success. We are testing with different sizes of fingertips to see whether the radius of the fingertip is actually affecting the chances of successful capture. And another potential good application would be to test with different materials of fingertips, because right now we have only 3D printed fingertips. We can try to capture the object with rubber fingertips, silicon fingertips, metallic fingertips, anything. So we can see how different friction affects the chances of successful capture.
Yeah, Nikos, thank you for the answer. That's very interesting. So, are we getting more questions from the audience?
We can run the demo once more.
Yeah, Nikos, why not? Why not? Let's try the demo once more.
So, and see if,
Yeah, might be some new people just come in. They can have a look. The exciting part.
so let's run it again and see if the robot can find out a better grasp. I think it's found a better grasp already, or at least a different one. So we can see, let's hope this time we have a successful grasp. It's starting well. This time it also failed.
We saw a.
That's okay.
We saw a spillage, right? We saw a spillage over there in the end. That seems like because maybe the material is also very important, right?
Yes, exactly. The selection of the material that we have to represent our target with is very important. And also the material tends to degrade with a prolonged exposure in the radiation environment of orbit.
Certainly.
And some the residue, and especially since these apogeic motors are essentially rocket stages and use the rocket stages, they tend to have some residue of the propellant in this nozzle. It would be very beneficial to have exactly this type of material, or a material with similar friction that we can emulate for our grasping purposes. This is a very exciting opportunity for future research, of course.
Thank you, Nikos. I think we have about 5 minutes for this run of the demo. We can show some other research we doing in parallel in our lab, especially on the orbital testbed. So that's another part. Okay, so for the motor in showing here as a target, that's we consider about as a non-cooperative target, and we're also working on the research with a cooperative target. As you can see from this video, what we're doing here, we actually using machine learning method to identify the target from 2D images rather than use point clouds data. And this is a very typical structure for the future on-orbit assembly missions, which means you have the Lego building blocks, very small ones. You want to put all the Lego building blocks into a big target. You need a connector which showing the black ring on the truss structure, and you also need the Lego itself, which is the white frame and showing on the target arm. So what this algorithm does is actually train the model of the target and learning the pose of the target, which means how far the target is and what's the angle facing to another connector on the service arm. So what it does is read the pose from the AI learning method from the database, and then find the pose of the target, and then do the assembly process, which have to be very accurately read the pose of the target. And as I mentioned before, the highlight of this research is we just using 2D image to read the distance as well as the angle of the target. So it's actually very challenging, very challenging. So Nikos, as I mentioned before, right, use point cloud have to face quite a lot of difficulties. For example, infrared light and some radiation, also extreme lighting condition in space, right?
Yes, exactly. This type of sensor that we use here with structured light is very difficult to work in microgravity conditions in space, actually. And this is because of the radiation that is prevalent in these environments, and the difference in the lighting conditions that happen at every orbit. Typically, these types of point clouds tend to be very noisy, so they have a lot of speckles, and they sometimes have missing parts or holes and things like that. The algorithm needs to find a way to work over these type of situations by actually examining what is the surface, the visible surface that it can work with. And we can always use other types of sensors to give us this point cloud. So we can get this point cloud by stereo cameras and even LiDAR sensors, which are some other types of laser sensors. And for the purpose of this demo, we're using a simple structured light sensor. But in orbit, as I said, we can use many other sensors for that.
Thank you, Nikos. We have about 2 minutes for to finish this round. So if the audience have any other questions, please feel free to ask. We're happy to answer.
Something else that we can say as well is that these type of nozzles are also part of satellites that are already in orbit. So this type of scenario can be used not only for deorbiting space debris, but also for satellite servicing, which is a very novel field. This type of nozzles represent a very good capturing point for the chasing robot, because they tend to be very rigid, and they have structure that can withstand a lot of different motions and variations in force. So this type of research, as it is here and with this testbed, can also be applied to the satellite servicing scenario, which again is a very promising and quite futuristic, I would say, type of research.
Okay, so is there any other questions we got from the audience? Because we have 1 minute for this round.
We have some very encouraging comments, so thank you for that.
Yeah, exactly. Oh, thank you, guys. Oh, we have a question came through, Nikos. Maybe we can use 10 minutes. 10 seconds to answer it. And so, what are you doing with the debris after the capturing them?
That's a very good question. There is a post-capture phase that we can simulate or emulate. Unfortunately, we don't do it in this type of experiments with a testbed, and it's called the rigidization phase. What happens after that is that the chasing arm needs to, let's say, make itself very rigid and apply a very strong connection with the target, so that it can ensure let's say, the successful deorbit and successful future tasks with the target. Basically, in this rigidization phase, the target and the satellite are matching their velocities and their angular momentums. So I hope this answers the question.
Yeah, I hope that answered the question. But also, if you ask a question about further what we're going to do, you can do servicing, you can do refueling. And for the nozzle, what you're going to do, you have to deorbit it or, capture it and recycle the materials. So hopefully that answers your question. So thank you, guys. We run out of time, but you can also come back, ask the same question. We're happy to give you more details in the next round, right, Nikos?
Exactly.
Okay, thank you, guys.
Thank you very much, everyone.
Hello, everyone. Welcome to Clean Space Robotic Active Debris Removal demo from Surrey Space Centre at University of Surrey. My name is Yang Gao. I'm Professor of Space Autonomous Systems, heading the STAR Lab, and here are my team.
Hi everyone, my name is Nikos Mavrakis and I'm a research fellow at Starlab working on robotic grasping for orbital applications.
Hi, my name is Richard and I'm the technical officer for Fairspace.
Hi, my name is Alexander Masowski. I'm a technician. I help researchers to run experiments.
Hello, my name is Daniel Johal. I'm a research fellow working at Starlab on Fairspace project. My job is how to drive spacecraft smartly. Okay, here you go, Yang.
So I'm going to give a very quick introduction about the background of the demo. So as people know, at the moment, our planet Earth is surrounded, orbited by a lot of space junk, or we call space debris. They could range from the span motor with nozzles, like the model I'm holding right now, or retired satellite, such as this kind of CubeSat system, and they're really harmful to the existing space assets, such as satellites that is providing satellite navigation or satellite TV. So it's important and critical for us to develop robotic and artificial intelligence solutions to help autonomously run dock and capture, remove this kind of type of object in orbit. So in this demo today, we're going to use the target, which is like the model I'm holding right now, because it's relatively more challenging for robotic grippers to capture because of the curvy surface. And also you're going to see different rounds of trials so that you can see how the decision-making systems on board the robot could decide in real time whether it's safe or not safe to proceed. And this is very important to secure the safety of our spacecraft equipped with the robotic arms. And I would also like to take the opportunity to thank Fairspace program, which funded the research behind this demo, as well as UK-RAS Network, who created the opportunity for us to engage with you guys today online live. Hope you enjoyed the demo. See you.
See you.
Okay, hi guys, it's Alex here. Me and Nikos will show you now a live demo from our testbed. As you can see at the video right now, we have a nozzle attached to one of the arm, and the other one is on the left side. You cannot see it because it's out of the view of the screen. But right now, I will give a mic to Nikos to explain a bit our experiment.
Hi everyone, so this is Nikos again, and I will describe a little bit what we're going to see today and what we expect to see today. And so we have a simulation first of all. As Yang mentioned before, we are going to see an example of active debris removal, and as you can see on your screen right now, we're going to show capturing and pulling back of an apogeic motor. An apogeic motor is the top part of the rocket that actually is tasked with placing the target, the payload, to its final orbit. It has not been designed to come back to Earth and deorbit naturally after it has placed the said payload to its orbit. And sometimes, in some cases, it can stay up to 25 years or more in orbit. And it has been recently been identified as one of the most, let's say, dangerous objects in low Earth orbit. The apogeic motor is the silver part of the video that you can see there. And the yellow part of the simulation is the chasing satellite, which is equipped with a robotic arm and a gripper. And the robotic arm is tasked with finding a very good grasping point of the apogeic motor, because as I said, the apogeic motor is not designed to be captured, so the robot needs to actually figure out a good way of capturing it. Let's say a successful grasping point. And the chasing robot does that by using what we call a point cloud. So a point cloud comes from shooting a light pattern, in our case, and measuring its distortion. So by measuring this distortion, we can translate this distortion of the light pattern to distance from the sensor. This distance from the sensor then gives us a point. And that's why we call it a point cloud, because basically it's a number of points that represent the distance of each part of the target from the camera. You can see an execution of the algorithm we have developed in StarLab in Surrey here, that it takes a point cloud and is able to come up with good grasping points. The grasping points are shown in the top left corner, and they are represented with these coordinate frames in green, red, and blue. As you can see, the algorithm is very fast, and some performance numbers we have is that in 0.2 seconds it can identify about 25 grasps, and the robot then picks the best grasp according to whether it is reachable or not, so whether it can actually reach this grasp. And yes, so in order to emulate the orbital environment, because in simulation and in a very controlled environment as the one you see now, it's relatively easy, but if we want to simulate or emulate the orbital conditions in Earth, it's more difficult. We use the testbed that we have here in StarLab, and the testbed is shown in our live feed that my colleague Alex will show you now. So the testbed, you can see it here. And Alex, do you want maybe to say a couple of things about the testbed, so what it consists of?
All right. Yeah, I can add that, as you can see here in the front of us, it's a traverser. So we have like a traverser to move one arm to each other. And then the one that you don't see right now is a chaser. So what I can do, I can show you how it moves to the first position to get a better, it will be closer to the target arm, which makes it all right. So yeah, so we have like traverser to move one arm to each other, but then you have a chaser arm, a target arm, which will be grasped by our manipulator. But I can still show you, because maybe first you can say about how the nozzle behaves and what we can see here.
Yes, definitely, Alex. So the target arm you can see on the right is equipped with a force torque sensor, which can identify any forces that are being applied to the target. And you can see how responsive is the system in simulating the orbital motion in this video. So this is me having some fun with that. And what happens there is that the force sensor picks up exactly these type of forces applied on the nozzle. And then we run these forces through a simulator that simulates the motion of the target as if it was in orbit, in a weightless environment. So this motion is fed back to the target arm, and you can see that the system is quite responsive. So Alex, if you want to play this video once more so we can see exactly how responsive it is, you can see that it reacts quite well to the touches and everything. So if you focus on the silver bit, on the shiny silver bit, and forget about the arm, this target appears as if it was in weightlessness, so in an orbital environment. And we use this type of target arm, this type of target behavior, to emulate weightlessness. So I think, are we guys ready to show the demo? I think maybe there is some minor trouble. Okay.
No, it's fine. It's working. So as you can see, as I mentioned before, we have a traverser which moves a chaser arm to a target arm. So that helps because from another video you can see we have a better point cloud, and it is in the range of the chaser arm. Where then, if I close now on the screen, the arm will be having the best position to start chasing the nozzle. And I can give now back to Nikos again.
Yes, this is actually what we call the proximity phase, where the chasing satellite is supposed to be in the range of a couple of meters to a couple of centimeters away from the target. And the robot is actually tasked in this phase to extract a very good grasping point, as we mentioned before. And right now, you can, if Alex wants to switch, yeah, there you can see it. You can actually see what the robot sees. So the top left panel of the image there shows the structured light sensor and the depth information that this structured light sensor extracts. The bottom left part shows the RGB camera that our sensor is equipped with. So you can have a more, let's say, realistic depiction of what the satellite would see in orbit. And these two together result in the point cloud that you can see in the right. As you can see, a very big part of the point cloud is also reflecting the wall, let's say, of our test bed. But this is something that is not taken into account in the grasping execution and in the calculation of the grasping point. So the robot just works with the point cloud of the nozzle. And I think now it's time maybe to execute our demo. So what you will see now happening is that the target arm will attempt to synthesize, to make, let's say, a good grasping point on the target nozzle. And after it does, it will move to the target grasping point. It will grasp the nozzle, and then will attempt to pull it back on a specified distance. If the chasing arm still retains a hold of the object for the whole duration of the pull, then we say that the grasp has been successful. Otherwise, if for any reason the chasing arm loses a hold of the object, then we say that the robot has failed to execute the capturing motion. So I think it's time now to execute our first demo. So I will be executing the demo now. You can see that the robot has found a successful grasping point, and it moves to that. So now it will attempt to capture the target, and let's see whether we'll have a successful grasp. That looks okay. That's okay.
Almost.
It happens. Like, it's very typical for these things to happen. And more often than not, we fail in our simulator to capture the target. This happens because of a lot of reasons that we'll explain in a while. But I think it's time that we do another execution. So whenever Alex is ready, we can do another execution. Let's see now whether the robot will be able to find. Okay, it has found another good grasping point. It moves on to execute the capture. So now it executes the capture, and it will start pulling. Okay, and in this situation now in this type of grasp, we can see that there was a successful grasp. So the robot was able to hold the object for the whole duration of the pull. And this is very exciting because, as I said, it does not happen quite often. And when it does, it gives us quite a good estimate of how to design this type of controllers and this type of AI methods for grasping and for actually successful debris removal. I think it would be good to actually execute it a third time to see whether there is a good chance of grasping again. So if you give me one moment, I will execute it.
Yeah, I think we will have soon time for some questions. So if you have any, please type them in the comments, and we'll answer them. So Nikos, what are you doing now?
So we can see that there is a grasp again. We can see that the robot starts pulling. Oh no, that slipped again. So anyway, this happens. It's very typical for these things to happen, as I said. And we have identified quite a couple of reasons for failure of grasps. The number one reason for a grasp that fails is the friction and the friction coefficient between the finger and the target surface. Right now, we are testing with 3D printed fingers, which is basically plastic, and the nozzle is made by aluminum. This yields a quite high coefficient of friction, and this can lead sometimes to not successful grasps. The second let's say, parameter that affects grasping is the application of a continuous grasping force. So we command the robot to apply a number of newtons. I think right now is about 180 newtons to the target. But the relative difference between the pose of the target and the robotic finger and the end effector of the target arm, the chaser arm, leads to the application of force not being constant. And sometimes we have the chasing robot relaxing its grip on the target. We need to, in some cases, we need to develop some more elaborate control methods that enable the chasing arm to touch the target in a more soft way, let's say, so that it minimizes the possibility of failure.
All right. I don't see any questions right now, so it is a time probably for them. And I must say, yeah,
I think, yes, if you have any questions, I think it's time to mention them now. We'll be very happy to answer them.
Yeah. Of course, we can mention another project we have as well, experiments. So we can show you a video prepared another day, but with a different target. So instead of nozzle, we have a frame, a subframe for a telescope in orbit. So what you can see, it's not the point cloud, but we have like a QR code, which the camera sees, and then it approaches to assemble and connect to effectors. I don't know. Can you, Nikos, say more about it?
Yes, definitely. You can see that the robot identifies the QR code as for the training purposes, and then it adjusts the orientation and does the final docking by estimating the pose from the deep learning system. And we use, as mentioned, we use QR codes for the training, so to gather data and train a deep learning method that can estimate the pose of a target with a simple RGB image, so without, let's say, another type of information. Another types of research we do in StarLab here is related to satellite servicing, because the nozzle that you saw before, as well as the algorithms that you can see in this screen with docking, they can be applied for the satellite servicing scenario, because these type of nozzles are not only part of space debris, but they are also part of active satellites in orbit right now. And they're also very capable and very structurally consistent targets and points of docking, and they have been used quite widely in tests and in some cases in some missions. So the research we showed about capturing the nozzle, as well as the research we show here in docking, they can also be used for the satellite servicing case. All right. I think if we have some questions from the audience, I think now is the time to let us know, and we can answer them. As soon as we have a couple of questions, we will answer them. But until then, we can mention some other things that we do and some other results of this research that we have identified. And as we let's say another parameter that affects how the grasp is successful or not is the curvature of the fingers. And in this particular demo right now, we are using spherical fingertips. The spherical fingertips have the advantage of yielding a more successful grasp, so a grasp that has a lot of chances of success. And just because their rounded shape matches the rounded shape of the nozzle. And especially the bigger they are, so the higher the chances of success.
Okay. Nikos, there is a question. Are this technology transferable to other sectors? Can you answer it?
Yes, definitely. So these type of technologies are definitely transferable to other sectors because at their core, they employ point clouds, which are widely used in most sectors, from agriculture to indoor robotics to extreme environments to industry, anything you can imagine. And the result of the grasping algorithm basically are just raw grasps. So these raw grasps can be applied to any type of scenario. There is nothing inherently spacey, let's say, about the grasping procedure. And it's very typical to have this type of processing to other domains as well. The deep learning for pose estimation can also be applied to other types of other industries. However, it has been developed with the lighting conditions and the targets that are met in a weightless environment in orbit. So it has, let's say, a higher difficulty of being transferred, but it's definitely possible. I hope this answers the question. We have still 1 minute as far as I can see. So if there is any final question, I think now it's the time to let us know.
Yeah, I think that was great. Thank you, Nikos. Oh, yeah, exactly. Thanks. And yeah, so we will have another demo in 5 minutes. So if anyone just joined us, please stay and or wait 5 minutes and join again. So probably now we have a break. Thank you.
Thank you again for being with us now, and see you later on for the next demo if you wish to stay.
Hello everyone, welcome to Clean Space Robotic Active Debris Removal demo from Surrey Space Centre at University of Surrey. My name is Yang Gao. I'm Professor of Space Autonomous Systems, heading the STAR Lab, and here are my team.
Hi everyone, my name is Nikos Mavrakis and I'm a research fellow at Starlab working on robotic grasping for orbital applications.
Hi, my name is Richard and I'm the technical officer for Fair Space.
Hi, my name is Aleksander Mosowski. I'm a technician. I help researchers to run experiments.
Hello, my name's Daniel Johal. I'm a research fellow working at Starlab on Fair Space project. My job is how to drive spacecraft smartly. Okay, here you go, Yang.
So I'm going to give a very quick introduction about the background of the demo. So as people know, at the moment, our planet Earth is surrounded, orbited by a lot of space junk, or we call space debris. They could range from the span motor with nozzles, like the model I'm holding right now, or retired satellite, such as this kind of CubeSat system, and they're really harmful to the existing space assets, such as satellites that is providing satellite navigation or satellite TV. So it's important and critical for us to develop robotic and artificial intelligence solutions to help autonomously run when dock and capture, remove this kind of type of object in orbit. So in this demo today, we're going to use the target, which is like the model I'm holding right now, because it's relatively more challenging for robotic grippers to capture because of the curvy surface. And also you're going to see different rounds of trials so that you can see how the decision-making systems on board the robot could decide in real time whether it's safe or not safe to proceed. And this is very important to secure the safety of our spacecraft equipped with the robotic arms. And I would also like to take the opportunity to thank Fair Space program, which funded the research behind this demo, as well as UK-RAS Network, who created the opportunity for us to engage with you guys today online live. Hope you enjoyed the demo. See you.
See you.
All right. Hi, everyone. Alexander is here again. And with Nikos, we'll show you the live demo. So Nikos will give you an introduction, please.
Hi everyone, this is Nikos again. And I will describe exactly what we're going to see in this demo. As mentioned by Yang before, we're going to see a demo of active debris removal in space. Well, not exactly in space, but in our lab. The target that we have, the piece of space debris that we have right now, is called an apogee kick motor. And it is basically the top part of a rocket that is launched into space. And its job is actually to place the target, the payload, in its final orbit after launch. You can see a simulation of what we're going to see here today. The apogee kick motor is this big silver shiny thing in the top left. And as I said, it places the target satellite into its final orbit, but it tends to stay in this final orbit after doing its job. Some of them tend to deorbit naturally, but even though when they do, it takes them about a couple of years to a couple of decades to deorbit. And I think some of them are still in orbit ever since the dawn of space exploration in the 60s. So as you can imagine, it's getting very crowded up there, and we need to develop some good methods for active debris removal. A key element of our technology here developed in Starlab is identified a good grasping point to capture the nozzle. The yellow part of the simulation is actually the chasing satellite. This satellite is equipped with a 6 degree of freedom robotic arm and a gripper. The task of this gripper is to identify a good grasping point for the nozzle of the apogee kick motor, capture it, and then pull it back in a specified distance. The way it actually is able to identify a good grasping point is by employing what we call a point cloud. So a point cloud is basically, in our case here, a light pattern that is shot to the target object, and this light pattern is distorted. So the sensor measures this distortion and translates it to distance from the sensor base. Each translated point from distance is then reflected to a point that represents the distance of a specific part of the target from the camera. You can see the point cloud in the top middle of this execution playing right now. So this is me just going around a 3D printed version of a nozzle. And right now you can see the grasping points generated in the top left part of the simulation. Each grasping point is represented with this coordinate frame that has red, yellow, and blue parts. And as you can see, the algorithm is quite fast in extracting grasping points. Some statistical, let's say, performance values we have is that it takes about 0.2 seconds to identify 25 potential grasps. And then out of these potential 25 potential grasps, the robot chooses the one that suits it best. So the one that it can reach best, the one it can actually, that it believes that it's best for it to capture. So it's very difficult, as you can see, to execute these type of grasping algorithms in simulation and let alone in orbit. So the way we do it in our test bed here is by employing robotic equipment, as you can see in our feed here. Alex, do you want to say something about our test bed? So what does it consist of?
Yeah, thank you very much, Nikos. Yes, so as you can see right now on screen, we have a target arm on the right, and actually on the left, you will just see a chaser arm, which is moving right now towards the nozzle. And the chaser arm has effector, which will grab a nozzle after, like Nikos will explain how he will do it. And our testbed actually has a traverser, which moves the arm. And then we have the UR5 arm, which manipulates effector and nozzle at the same time. So as you can see, it's dark there. We try to simulate space conditions with only one source of light. So it helps with the point clouds, which was mentioned before by Nikos. So now I give Nikos mic to explain the grasping.
Thank you, Alex. So a little bit about the target arm first. As was mentioned, the target arm is there to emulate the behavior of the target in a weightless environment, so as if it was in orbit with respect to the lack of gravity. And you can see that right now, Alex will give you a demonstration of how this target arm behaves. And you can see this is me having some fun with this system. So the target arm is, it has a force torque sensor, which is able to read all the force I am applying on every push there. This force is then transferred to a simulator that simulates the orbital dynamics and the orbital motion of the target as if it was in space. This motion is then fed back to the target arm and effector, and you can see that in a very responsive and fast way. You can see that the system responds to quite a lot of my taps there. And if you focus on the big, shiny part of the video there and ignore, let's say, the rest of the robotic equipment, you can imagine that this target is floating in orbit. which is basically more than enough for emulating these weightless conditions for our experiments. Alex will show you again the testbed now, and we can discuss a little bit more about the situation of the testbed right now. So what are we exactly seeing?
Okay. All right. So we're heading back to our testbed. So right now, the arm is in position to see a nozzle with a quite nice point cloud, as you can see on the picture. I know, maybe Nikos, you can say more about it as well.
Yes, definitely. So you can see that in the top left part, it is this depth information that we get from the structured light projection from the sensor to the target. And in the bottom left part, we can see an RGB feed of our camera to give you more of an indication of what a real robot would see in orbit in this case. These two feeds, so the RGB feed and the laser feed, result to the point cloud you can see in the right. You can see a very huge chunk of the point cloud is dominated by the wall in the back of our testbed. This is something we cannot avoid, but for the purpose of the estimation of the good grasping point, it is ignored by our algorithm. So the algorithm focuses only on the shining nozzle you can see there. And if Alex, if you can switch a little bit to the view of the testbed, so we can explain exactly what we see here. So right now, we are what we call in the proximity phase. So the proximity phase, when there is let's say a robot that captures a target in orbit, is between a couple of meters and a couple of centimeters away from the target. And the robots at this point is tasked with identifying good grasping points and perhaps some other properties of the target, such as mass, relative pose, orbital velocity, and things like that. Yeah, I think, Alex, it is time to run our first demo. So what we're going to see now in this demo is the left arm attempting to capture the nozzle. So the robot will find a good grasping point, reach this grasping point, close its gripper, and pull the target back for a specified distance. If the robot still holds the target after the execution of the pulling motion, then we say that the grasp is successful. But if at any point the target slides from the grip of the gripper, then we say that the grasp has failed. We're going to run a couple of executions. Let's hope some of them will actually succeed, but more often than not, they tend to fail due to a lot of reasons that we'll explain in a while. So I will execute the first run of the experiment.
So finger crossed.
So yes, exactly, finger crossed.
So right now, Nikos started his approach to the nozzle. His software found the right grasping points, as you can see, on the nozzle. And we'll try to pull it. And as you can see, it actually was released before the move finished. So that was failure, I understand, right?
Yes, exactly. That was a failed grasp, which is fine. As I said, it tends to fail more often than it does succeed. There is quite a number of reasons for it happening. Some of them are related to the friction coefficient between the finger and the nozzle, which in this case is a friction between a 3D printed finger, which is basically plastic, to a nozzle that is made from aluminum. And I think it's a very good idea to run a second demo now. So what do you think, Alex?
Yes, that's correct. So try another round. And okay, so you should see like our arm is trying to think about where should grab the nozzle. And I think right now,
I can identify the different
Oh, yeah.
grasping point,
Okay,
which
we have
is
it.
good. So I think now it reaches on for the capture.
Yeah, hopefully this time it will be successfully.
I think, yes, this time, yeah, this time is successful. That's very
Well
good.
done, Nikos. By the way, this is Daniel. I'll just write back.
Yeah, this is Daniel again, our colleague. And you can see, you can see that the robots are now returning to their original positions. It's very good that the grasp succeeds, because when it does, we can identify exactly why it succeeded, and then we can try to build our algorithms and our control methods based on these results. Yes, I believe maybe it's time for a third experiment that we can see. So
Okay,
if
yes.
you give me a couple of seconds.
Yeah, no worries. So I think it's time for any question. If anyone from audience has a question, it's a good time to type it in the comments, so we can answer it after Nikos' third try.
Okay, we can see again another point.
Okay, let me show it.
Let's see.
Okay, yeah, we have now the view of our testbed. Oh,
that
was it
was-
successful? Wow, Nikos, I think
That was another successful grasp, which is very good. I think I'm quite surprised because this was 2 out of 3, right? That's very good. Typically, we get like 1 out of 5 or whatever. That's very good to know, actually. So as Alex said, it's time, if you have any questions, that's a very good time to actually start typing them, and we can answer them.
Okay. Yeah. I mean, it doesn't happen that often that we have that many success. So I think it's quite. Oh, actually, Nikos, I have actually a few questions for you. So prepared yourself.
Oh, we have already a couple of questions there,
Yeah.
as I can see.
So there was, of course, a question about wouldn't debris eventually fall down to Earth?
Yeah, I can answer that question.
I think, yeah, that's a question for Daniel, who is our space expert here.
Well, that's overcompromise. Anyway, okay, cool. So depends the orbit. So it depends how far the debris from the Earth. You know, it depends if they are designed to be the orbitable or not. For example, if there's a really large structure at very high the altitude, it can take up about a few years or even 20, 40 years to do the orbit. So that won't be eventually fall down to the Earth. You need to have some method, the orbiting method. For example, you can have a workable thruster to push the orbit, to push the objects back to the very close to orbit, to the deorbiting altitude. Or you can have a send a robot to grasp it, like what we're doing here. Because loads of early stage space objects or space missions, they not really consider the orbiting. They're not really expecting, you know, our orbits getting so congested these days. So that's why for the big agency like ESA are pushing forward a clean space agenda, just trying to be more responsible. You know, when you're launching a spacecraft, we're launching orbit, objecting to orbit, you have to consider how you recycle them. So that's one of the things we need to consider. There are some of the design these days, they fly really low, like maybe 300 kilometers or even lower. So they will be eventually naturally falling down to the Earth, maybe within a very short lifetime because they are designed so. So hopefully that answers your question. I think, Alex, we have another question, right?
Okay, yeah, we have another question.
Do you want to highlight that question as well?
All right. So, how do extreme conditions, for example,
Makes it
microgravity-
grow. Oh,
Yeah.
that's a good question for Nikos.
Challenging.
That's indeed a very nice question, because there is a lot of reasons that this grasping task is very challenging, and some of them have been identified as well in the question. So let's say the radiation and the difference in the lighting conditions tend to create some holes and some noise, let's say, and missing parts on the point cloud. Especially with this type of sensor that we use right now in our testbed, as it is, it would not work in an orbital environment because it has not been designed for that. The structured light that it emits is scattered very easily in these type of conditions. In space, to extract a point cloud, other missions and other experiments use either a stereo camera, which is basically two cameras that identify features on the RGB image and then translate these features into depth information. Or there is some proposals to use a LiDAR sensor, which is basically another type of laser sensor that is more focused and tends to have, let's say, less chances of having a scatter. But with respect to the microgravity part, the difficulty is in the control bit right now and in the contact phase. So when we have a contact with the gripper, if it is on Earth, then we can take gravity into advantage and implement some grasping algorithms that match this pull of the gravity. In orbit, it's very difficult because we need to approach the target in a very soft manner, in a very soft touch. If we approach it very hard, then there is a chance that not only we let's say, push away the target, but we also push away the satellite itself as well, so our body, due to the reactive forces that are being induced. I hope this answers this question. So we still have 2 minutes for this demo, as far as I can see.
Yes. So we can show you maybe another video from another experiment. It's a different approach. I think actually that's Daniel's approach for assembly in orbit. Could you explain?
Yeah, this is the work with Aaron, my colleague, and me. It basically, as probably Nikos explained before, the target we showed you before is considered as a uncooperative target. But that's only the one thing about the space about orbital robotics. Another target type is generally for on-orbit assembly, and they are more like cooperative, which means you can control them or they are fixed at a position. So we also have done some experiment over those targets, which are cooperative target, generally for on-orbit assembly. And what we can use, we actually use 2D images to tell the position and 3D location of the target. So thanks for the AI algorithms, we are able to do that. And this is very beneficial because we don't rely on the point clouds or 3D images, those more complex visual sensors, which can be more costly and efficient. So for this algorithm, we using 2D image, so to tell the pose of the target, and we run the assembly algorithms to automatically make the docking. And this is a very typical structure over here for future space missions, such as assembly a large telescope in space. And the black ring, the black structure mechanism you saw from the picture is actually a universal connector, which designed for standardized building blocks for future missions. For example, you can imagine if we do assembly of really large structure in space, we have to send and use very small building blocks like Lego. So this is one of Lego pieces you just saying. So hopefully this very interesting demo for you. We still have 5 minutes. If you have any more questions, feel free to ask. And this is the last chance because this is our last run. Yeah, is any questions? But thanks for that question. Very interesting. Okay, now we have another camera active now. It's actually the camera showing our
either the result of collisions in orbit or the result of, let's say, tended to do a lot of damage. I'm pretty sure you all have seen the very recent footage of the Canadarm that was pierced from end to end by such a type of debris. And it's very difficult because even though they tend to naturally deorbit quite fast, let's say, it's very difficult to actually track them, identify them, and capture them, and then get rid of them in some meaningful way. I would say that from the largest pieces of space debris, the most dangerous one are these types of spent rocket stages, and especially some of them that tend to be in the range of a couple of meters, let's say, big, because sometimes they may have propellant left over, and sometimes they have a residue in the propellant in the nozzle, which tends to create extra debris. It's actually a very challenging problem, and as you can see, there is a lot of the ways that we can approach it. I hope this answers the question.
Yeah, sure.
I think it's time now, so everyone
Nikos,
from
thank you.
Starlab.
Yeah, sorry, we had a small technical issue before. So I just repeat what I said before. We all had our jabs already, and we all follow the rule for the COVID. We're all in a working bubble. So so thank you for some people just mentioned about that before, but we're all safe. We're all following the rule really well. So I'll pass the mic to Professor Gao, and she will have some.
No, I just to appreciate everybody's participation this afternoon. Thank you so very much. And thanks all the team members who put really hard work into this. Hope you enjoyed it. Stay in touch with us. Okay, bye.
Thank you.
Bye.